everybody, today we're going to talk about applications of concavity and the second derivative test. So first I have a little picture for you, and I want you to see it kind of looks like an S, so we call it an S curve. And what it shows is at the beginning there's this growth. The growth rate was increasing, but there comes to be a point where the growth rate starts to decrease. So we have this quick little increase at the beginning, and then the concavity change. So that concave up was increasing at an increasing rate, and then concave down is increasing at a decreasing rate. So this point where things switch will be really important. We'll have a couple of things to say about it. First, I thought we'd look at something we're all familiar with, which would be COVID. So I'm starting at looking at COVID cases and deaths in Italy. And we all remember, back about a year ago, a little bit more, when COVID first came out, it was increasing at a really rapid rate, and everybody was talking about flattening the curve. And I thought the Italian graph shows really well what flatten the curve looks like. It took that increasing at an increasing rate, and you can see it kind of did stay pretty flat for a period of time. Then all of a sudden, it started increasing again. Now let's watch what happened. When you're first looking at it, so let's say we're January to about August, and you can't see exactly where it happened, but it's concave down. And then there's a place probably around August where it became concave up again, so this increase became big, right? So there's our change from concave down, where it was slow and kind of flattened, to up, where it's getting bigger. And then you can see it happened again, where it became concave down, and then once again, it went up. This would be Delta variant. Let's change to a different country. So now I'm on the United States, and you can see something similar happened. We had this big increase that was happening, and then at some point it started to slow down, and then it increased again. Now, something particular about these types of graphs is they're always increasing. When you're doing a cumulative graph, where you're keeping track of what was in the past and every new case gets added to before, it can't ever be a decreasing. So these are only increasing graphs. But to differentiate between when they're increasing really quickly or increasing really slowly, we can look at the concavity. In business, we call this the point of diminishing returns. So the point of diminishing returns occurs at the inflection point. It's where the function changes from increasing at an increasing rate to increasing at a decreasing rate. Let's look at an example to see how that would work. So we have a company estimates it will sell N of X units of a product after spending X thousand dollars on advertising, as given by N of X is negative 0.5 x to the fourth plus 26 x cubed minus 360 x squared plus 20,000, where x is greater than or equal to 15 and less than or equal to 24. We want to know when the rate of change of sales is increasing and when is it decreasing, what's the point of diminishing returns, and the maximum rate of change of sales. We'll start by taking the derivative. N prime of x is equal to, I have negative 0.5 x to the fourth. The 4 comes down, that's negative 2x cubed. We have 26x cubed is 78x squared. Minus 360x squared becomes negative 720x. And then the 20,000 is gone. Because we want to find when the sales are increasing and when they're decreasing, we will need to find the critical points. So we're going to look at negative 2x cubed plus 78x squared minus 720x and factor out a negative 2x. That'll give us x squared minus 39x plus 360. I have negative 2x. And then I'm looking for factors of 360 that give me 39. This can be factored into x minus 15 times x minus 24. Set that equal to 0. You get x is 15. X is 24, and the beginning x is 0. Now let's pay attention to our domain. Our domain happened to be 15 to 24, so we know we can't use the 0, and we see there's no place that's going to switch between 15 and 24. So whatever happens, it will be consistent between 15 and 24. To find the point of diminishing returns, we're going to take the second derivative. So let's go back to the first derivative. Negative 2x cubed is negative 6x squared. 78x squared gives me 156x minus 720. We can take out a negative 6. I have x squared minus 26x plus 120. Factors of 120 that give me 26 are x minus 6 and x minus 20. That says x would be 6 and x would be 20. Again, I'm going to refer back to the domain and say 6 is not an option, but 20 is. To check the concavity, we need to break up the domain. So we start at 15, we go to 20, then from 20, we go to 24, and we're going to pick a test point. Let's say we pick 16, and let's pick 21. You're going to plug that into the second derivative. Don't forget the negative 6 out front. I have x minus 6 and x minus 20. So for the 16, I have negative 6. 16 minus 6 is positive. 16 minus 20 is negative. So this is positive. This is concave up. And then with 21, I have negative 6, which is negative. Then I have 21 minus 6 is positive. 21 minus 20 is positive. Negative, positive, positive is negative. This is concave down. So picture that concave up, switching to concave down. Here's our point of diminishing returns. So I can tell that this is my inflection point because concavity changed. It also gives me the second part that it asked, which was the maximum rate of change of the sales would be 20.